Alrighty, welcome to the Chapter 21 video. This one is going to be about, I guess I should slide over to it, electric fields, and then later on we're going to get to a section on potential energy and voltage. But before that, I just want to briefly refresh in your memory what we talked about last time so that when we talk about the new stuff, you'll be able to put it all together. So before this, you learned about electric charge. Some of the key things were that the units of charge were coulombs, and the fundamental unit in nature is actually 1 electron, or 1 positive charge, which is on 1 proton. And those are equivalent to 1.6 times 10 to the negative 19th coulombs. You should memorize this number. We should already have it memorized, but you should definitely memorize this conversion factor because you're going to need to utilize it pretty frequently because you might be dealing with a small number of electrons or protons in an atom. Second thing is that charge is conserved, so the total charge at the beginning equals the total charge at the end. But if you have positive and negative, they can kind of balance or cancel each other out. Lastly, this force equation is for Coulomb's law. Well, that's what it's called, Coulomb's law. It allows you to find the force between 2 point charges. This only works between 2 individual point charges. If you have a whole array of them, then you have to use this formula multiple times for each different pair of charges. And the k here is the constant of proportionality. You can round that to 9 times 10 to the 9th. Q1 and Q2 are the two charges, and r is the distance between them. It's important to remember the difference between charging by induction and an induced dipole. I'm not going to re-explain it, but if you don't remember that, go back to the other video and watch the 5-minute segment on the difference between charging by induction versus induced dipole and what they are and how they work. Alright, so we're going to start this off by talking about the electric field. It's kind of a cool concept, I guess, basically invented by man to help ourselves out and make our math easier, and we'll get right to it. So, the electric field definition. The definition is the total force exerted on a charge divided by the size of that charge. So it makes sense that if you've got a whole bunch of charges around, if you put a bigger charge into it, it will experience a bigger force, because in Coulomb's law you have Q1 times Q2, so the force and the charge are linearly related. If one goes up, the other goes up. So the electric field is a ratio of the force to the charge. So it's telling you something not about that particular charge itself, but about the surrounding environment of that charge. All the other things that are causing a force on, say, your charge, are independent of what your charge is. So if you changed your charge just a little bit, the force would change, but all the surrounding properties, which we're going to call the electric field, would not change. So the electric field is caused by everything else around your charge, but not caused by your charge itself. And so the force that your charge will experience is equal to the electric field caused by everything else multiplied by your charge. So the definition is E equals F over Q, but typically I always write it like this. F electric is QE. This is how I remember it. This is how I will refer to it. This is how I will start with this equation in all problems and then rearrange from there as needed. So this gives you the magnitude of the force and the magnitude of the electric field, but not the direction. So to find the direction, you have to use common sense and the law that opposites attract and like charges repel. So if the positive charge is your test charge, then we've defined, or we will define, or we are currently defining, that the force direction is the same as the electric field direction. Remember, these are vectors. So the direction of the electric field and the direction of the force will be the same for positive charges. Again, it makes sense if this is positive and this is positive and this is positive. Everything lines up, so to speak. Now, if you had a negative charge, then one is pointing this way, the other one is pointing opposite direction. So negative charges, the force is opposite the electric field. So positive charges, if you want to think of the electric field as a river pointing a certain direction, if you drop a positive charge into a river, it'll go with the river. If you drop a negative charge into an electric field river, so to speak, it'll go upstream opposite direction. Okay? A concept to help you kind of get this idea of electric fields in your head is we've already learned about fields and their effect in terms of gravity. So on Earth's surface, there's gravity everywhere. If I pick up some pen, there's a property of space right here in front of my head that there's a gravitational field pointing downward. So it's not doing anything, though, unless I put something there. So if I put a pin here and I let go, gravity exerts a force on that object and pulls it downward. So you could have a region in space where there's an electric field. Okay? Maybe you can't see it, you can't touch it, nothing happens. But if you were to put a charge there and let go, then that charge would accelerate with the field if it was positive, or opposite direction if it was negative. So the electric field is a property of space caused by things external to that that will have an effect on charges if you put the charges there. Okay, I probably just explained most of this, so concept, instead of calculating the force, okay, so the idea here is that you can find out this property of space even if you don't know what you're going to put there. So on Earth's surface, we know that the acceleration is 9.8 meters per second squared everywhere. That's very useful for us to know. It doesn't matter if I have a small pen or a giant bowling ball. The acceleration is going to be the same in both cases. So it's good to find a property of space independent of what you put there. So it's kind of like factoring in math class. This is just going to be an analogy, but the forces is k q1 q2 over r squared, and you might have the same k in all cases, and your charge q1 is the same, and r squared, these could all be, each charge could be different, and the distances could all be different, depending on where the charges are. But the one thing that's the same in all three cases is your charge, your charge, your charge. So when you're using Coulomb's law between lots of different charges and different distances, in all cases, your charge is the same in all three. So you could factor your charge out, and what you'd be left with is like kq1 over r1 squared, kq2 over r2 squared, kq3 over r3 squared, etc., as many charges as you have. And so the net effect of all of those things, the other charges and how far away they are, is what gives you your electric field. So if you multiply all the field times the charge, you'll get the force. So again, F equals QE. It works for a single charge, it works in a uniform field, it works in a very complex field. So if you know the electric field, you can immediately get the force on the particle, which is very convenient. So you can find the electric field values even if you don't know what charge is going to be put there. Okay, so let's go through a quick derivation of what is the formula for the electric field caused by a point charge. So we know the force is exerted because we know Coulomb's law, and we know the electric field is the force per charge. So if we just divide this entire equation by Q, and we'll treat it as Q2 as the unknown, so if we were to just divide by Q2, this will cancel out, leaving behind the electric field of a point charge is everything else. The K, the Q1, and the R squared. Okay, so this is an important formula to write down. The electric field caused by a point charge is kq1 over r squared. What that means is the electric field very close to it is quite strong, and as you get farther away, the electric field gets weaker and weaker and weaker. So this tells you the magnitude only. So this formula, in fact, I think all the formulas in this chapter, just give you magnitude, and then you need to figure out the direction using common sense. So if you have a positive charge, the direction of the E field, it tells you which way the force would be on a positive charge. So if I put a little positive charge right here, which way would the force be? It would be radially away because it's repelling, so it's this way. If I put a positive charge right here, it would point this way. If I put a positive charge right here, it would point this way. If I put one here, it would point this way. Here, it would point this way. And you can just go around and around and around. And you can see that if I have a single positive charge in the middle, and that's all I have, anywhere around it that I put a second positive charge, it would be pushed away, and so the electric field points radially away in all directions. If I had a negative charge, you can think about that, any positive charge would be pulled inward towards it, so the electric field for a negative charge is radially inward. And now you can imagine that when you have multiple charges all together in the same kind of picture, that things can get a lot more messy. And so I'm not going to draw those myself by hand, but I do have some pictures already brought up that I want to show you. Hold on. All you have is radially away, simple negative charge. All you have is radially inward. Here you have a positive charge here and a negative charge here, and the lines are pointing away from the positive and towards the negative, but in between you get some weird behavior where they kind of curl around and connect. And why that can happen is because, remember, these arrows point the direction that a positive charge will experience a force. So if the positive charge is over here, it's very close to this positive, and it's going to repel in almost a straight line, because this one is so far away it has a small effect. And likewise, if it's over here, it's going to get pulled inward in mostly a straight line because this one has a small effect. But if you're in between, you're feeling the effect of both of these guys combined. And so like say right here, this one is trying to push you away that way. This one is trying to pull you in this way. And so the net effect is kind of in between, that one being away and that one being towards, and then this one is in between to the side. And so all these here, where they bend and curve, is an effect of both of those vectors being added as vectors. Okay, let me look at these two. This one is even more dramatic. So here, these are, this one is a little bit more charged than this one, but they're close to being the same charge. This one, this F1 has way more charges than this E here. And this one is positive again, this one is negative again. So because it has so much more positive charge, the amount of repulsion away is going to be a lot higher than the amount of attraction towards this one. So even if you're over here on this side, you're closer to this one, but this charge is so much bigger that it can still push you away that way. And so the number of lines that you draw, when you draw these kind of diagrams, the number of lines you draw should be proportional to the charge. So the bigger the charge, the more lines you have coming off, which shows that you're getting pushed radially away. Here you have 3 charges, all the same. These are all positive. So no matter where you are, you're getting pushed away. If you're in between them, you get pushed up or down. If you're exactly perfectly on the line, on the axis joining them, you're in an unstable equilibrium position. So you've got huge forces pushing this way and this way. And if you move just a smidge up, you'll get shot upward. If you move just a smidge down, you'll get shot downward. But if you stay on that line, you are in equilibrium. So it's called unstable because it's equilibrium, but as soon as you disturb it a little bit, it doesn't go back to where it was. It shoots off in an unstable trajectory. Okay, so there's some examples. Let's see what other examples we got. Very much the same thing, just labeled positive and negative instead of what they were. How about this one? It's positive and negative, lines connecting. Here these are equal charge, so it's a nice symmetrical pattern on both sides. Notice along that when you're halfway between, along this line, the forces are always side to side because one is attracting and one is repelling at the same angle. This is a really important thing. This is called a parallel plate capacitor. I'm going to talk about it a little bit later on, but let's talk about the shape of it and the look of it now, so when we get to it later, it'll make sense. What you have here is a row of all positive charges, and what you have here is a row of all negative charges. So since the electric field points away from positive and towards negative, these charges are all having forces push away, and these charges are all having forces push towards. Hands might have been backwards because the camera flips things. But anyways, the net effect is that the lines point parallel and from positive to negative. So what this creates inside is called a uniform electric field. It means the direction is always pointing the same direction and the strength is the same. So you can go anywhere in here and it'll be a uniform field. This is just like gravity on Earth's surface. So on Earth's surface, gravity is a uniform field. It's always pointing down and its strength is always 9.8. If you compare that to over here, it's very different. Like if you're right here, you have a very weak field. If you're here, you have a very strong field. So as something moves around, the strength of the force on it is going to be changing. So this is a lot more complicated behavior to calculate and predict trajectories of things. If something is in here, it literally is going to behave just like an object thrown, for example, a ball thrown through gravitational force on Earth's surface. So if you have someone, imagine tilting this on its side. If you have someone throw a ball, it'll take a nice parabolic path like that as it gets pushed towards that plate, something like that. Okay, see if I have one more. Here's something super crazy. So when you have different size charges, mixed positive and negative in weird orientations, you need to use a computer program essentially to calculate the trajectory of these field lines. And so you can see that you get some weird stuff happening, and it's really hard to predict. So typically you wouldn't ever be asked to draw these yourself, but if given a picture, you should be able to explain that says like, okay, if I were to put a positive charge right here, it would go along, or there would be a force along this direction because it's being repelled by these three. Even though it's being attracted by this guy, it kind of tilts it off course, etc. All right. That's enough of those, but they should give you an idea of the directionality of the electric field. It tells you the direction of the force on a positive charge. Oh, it took us to the beginning. Sorry about that. Let me zoom ahead. Okay, so let's do a quick sample problem. The electric field 2 centimeters away from a small object points towards the object and has a strength given by 180,000 newtons per coulomb. What is the object's charge? So we've got a little object here. The field points radially towards it. Oh, well, towards it. So no matter where we are, we're pointing in like this. So 2 centimeters away, say 2 centimeters, we've got an E field at this point. So the formula is kq over r squared. What is the object's charge? So we need to solve this for q. Multiply r squared over here. So we get er squared. Divide both sides by the k equals q. Okay, I'm going to leave it at that just for the sake of moving more quickly through these notes. But if you plug in the distance is 2 centimeters, converting units, E is this number here, and K is 9 times 10 to the 9th, you can find the charge. And you should know that the charge is negative based on the directionality. This equation will not give you out a negative, but you have to know that because the electric field lines are pointing towards this object, this charge, that the electric field points towards a negative, therefore it's negative. Okay, example problem. Say you found a coin that has a mass 15 grams, and you put it into an electric field with strength 600 newtons per coulomb pointing vertically upward. Okay, so here's your E field. I should have put the word uniform in there, but it's a uniform E field pointing upward at 600 newtons per coulomb. How many electrons or protons would you need to add or remove from the coin in order to make it hover? We want this coin to kind of float right here. Okay, so it's going to have the force of gravity downward on it, and in order to hover, it's going to need a force electric pointing upward. Okay, we want the electric force to point the same direction as the electric field. So this right here, this is the electric field pointing upward. Remember, the E field points the same direction as the force for a positive charge. So we need this charge to be positive. Okay, and we know the formula is F electric equals QE. So we can figure out how much charge we need if we divide both sides by E. Divide both sides by E. This is a subscript, so those don't cancel. So we got the force divided by the electric field equals the charge. The force has to balance this force, which is mg. So the electric force has to balance mg divided by E. And there's our formula for the amount of charge. Now that's going to give us an answer in coulombs. So once you plug in 15 grams, you have to convert that to kilograms. So 0.015 kilograms. That's your mass. Gravity is 9.8. And the electric field is 600. Okay. As you see this coulombs, newtons, meters, gravities, kilograms, everything is going to cancel except coulombs, so we'll get our charge as some amount of coulombs. Then we're going to need to convert that to electric charge by multiplying by 1 over 1.6 times 10 to the negative 19th, because 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. So plug in these numbers in a calculator, get the amount of coulombs, then multiply, or really you're dividing by this conversion factor to get your final answer. Sorry that my directionality is going the wrong way, but that'll get your final answer. Okay, let's look at some properties of electric field lines. You've already seen lots of pictures, so these should come as no surprise. Number 1, the direction of the electric field tells you, well, the picture tells you the direction of the electric field at any point. So whichever way the arrow is going, or the line is curving, that's the direction of the electric field. Second thing is, the lines always point away from positive charges and towards negative charges. Third thing is, they start on positives and they end on negatives, or they start on positives and they go radially outward and don't end at all. So if you have a picture with all positives, they might just go from the positive out towards the edge of the screen, which shows that if you were to put a positive charge there, it would just get pushed away infinitely far. And likewise, if you have only negatives, or more negatives, they can come inward, which means any positive charge around it would be drawn and sucked inward. But if you have equal amounts of positive and negative, then the line should start on the positive and end on the negative. They're always smooth curves. They never have sharp corners and they never cross. That's because what they're telling you is the direction of the force. And you can imagine if you had two lines that crossed, you'd be simultaneously saying the force is going that way and the force is going that way, but you know that the net force can only point in one direction, so the lines must be smooth and they must not cross. The number of lines going into or leaving any charge is proportional to its size. That's something I had said on the previous slide when we were looking at the pictures. The bigger the charge is, the more lines you can draw coming off of it. It doesn't matter how many you pick, but they have to be proportional. So if you have one charge that's 3 times bigger than another charge, you got to draw 3 times more lines coming out of or going into the bigger charge. Usually I try to draw like 4. If I have something that's a 3-to-1 ratio, I'll do 12 and 4. If I just have 2 things equally charged, I'll try to draw 8 and 8, or maybe 6 and 6, something like that. The idea is not that you have a perfect representation of the electric field, it's that you have a general sense of where things are going to be moving. Lastly is the density of the lines, which means how close they are together, tells you how strong the electric field is. And this makes sense because all the lines are starting off of the same point, so they start off really close, and when you're very close to the object, you have a high electric field. And as you get farther away, they spread out, which means when you get farther away from a charge, you have a smaller field. Okay, practice drawing E field. I'm going to skip this slide because I already drew a couple, and we looked at a lot of pictures online. Uniform E field. So the word uniform is a very important word, and here's what it means. Constant magnitude, constant direction. So the way that you would draw this is a bunch of parallel lines, all the same length. So the length of any line is proportional to the size. So remember, if it's force, or if it's electric field, or if it's velocity, doesn't matter. So parallel lines of same length is the way that you would draw a uniform field, which means if you put anything anywhere in here, it's just the same amount of force as anywhere else. So if I put a positive charge here, or here, or here, or here, or here, all of these guys would experience the same total force, and it would be given by QE. Whatever the charge is, multiplied by the strength of that electric field, which is the same everywhere in there. Okay, so a super common example is the paraplate capacitor. That's the picture I showed you earlier with one row of positive and one row of negative. So you have 2 flat conducting plates that have opposite charges. So based on this picture that I just drew here, if we go back one, this whole side, we're pointing away, this would be the positive side, and this whole side here, if it was 2 metal plates, this side would be the negative side. And then it makes sense if you think about it. Any positive charge is trying to get away from these positives and move towards these negatives. So the electric field is not some kind of brand new concept that you have to add to your list of things to memorize. It's a natural consequence of the fact that positives repel other positives and positives attract to negatives. So the electric field lines just tell you where the charge would naturally want to go anyways. Okay, so what about conductors? If you put a conductor into an electric field, the electric field is trying to put a force on all of those charges that the conductor itself is made of. So if you put an electric field, say going this way, then you put a giant conductor in the middle of it, all the positives are going to be pushed over to this side, and the negatives on this side, and then what's going to happen is they're going to create their own E field going the other way due to that charge separation. And the superposition principle says if you have an E field going this way and an E field going this way, they're vectors, so you can add them up. And the net effect is that inside you've got an E field that's 0, and then outside you'll have the E field, and it will actually, it'll cause it to kind of bend a little bit, like this. So locally it will bend in and then bend out, and then from far away not much will happen. It will just go straight past. But inside the conductor, the electric field will be 0. And it's easy to remember this because if the electric field was not equal to 0, there would be a force moving the charges, and they'll just keep moving and moving and moving until they set up the exact perfect conditions to no longer move, which means the electric field is 0. This is valuable or useful to us because anytime you have something that you want to protect from external electrical stuff, you have to just encase it with a conductor. So that's why, for example, your computer, it has a giant metal case all the way around it. If there's some large amount of electromagnetic radiation that all of a sudden hits it, instead of frying all the components on the inside, the charges in the case itself can move and redistribute to mitigate any external electric fields. So this could represent the case, and the charges in the outside will move around so that the inside electric field stays at 0. What if the conductor itself is charged? What about the direction of the E field at the edges of the conductor? Well, I'll tell you what. If the conductor itself is charged, the inside will still have electric field of 0, but the electric field outside will be shifted or affected by it. We won't go into the details unless you want to come in into office hours. And the direction of the E field at the edges, the electric field always comes in perpendicular. So this is going to be a right angle. The reason it's always a right angle is because you can imagine a flat surface. If you had a vector coming in at an angle, it would have a component that was horizontal. And if there was a horizontal component of the force, those electrons would slide side to side, and they'll keep sliding until there's no more force. And the point at which there's no force is when the electric field points radially perpendicular to them so that there's no side-to-side force. That's not really critical. These last two things are not critical to know at all. I just put them in here because it's interesting information. Okay, sample problem. Let's find the strength and direction of the electric field at point P. So we're not finding any forces. There's not anything actually located here, but we don't know the electric field at this location in space. Specify the angle above or below the horizontal. So here's a positive charge. The electric field will point away from it. So the electric field right here will go this way, caused by this guy. Over here we've got electric field also pointing away. Radially away here, let's draw a line connecting it, is going to be this way. And this one is not quite as long. It's a little bit shorter. And the reason that this force is, or this electric field, let's call this E2, and let's call this E1, let's call this Q1, let's call this Q2. The reason E2 caused by Q2 is smaller is because it's farther away. Okay, so to solve this problem, we want to find the total of E1, the total of E2. We're going to need to break E2 into its vector components. We can call this EX and EY. We can have to find this angle, which is the same as this angle. So this problem is actually quite a bit of intensity here. Tracy, your phone went off. Sorry about that. This one is a bit of intensity because we're going to have two things at vectors. So if you're in this class for concept only, I'll say you can just pay attention to the idea here, but you won't have to solve these. If you're in this class for math, you should have to solve these. So first we need to find this distance away. This distance here, use Pythagorean theorem of 5 and a 10. 10 squared is 100, 5 squared is 25, so this is a square root of 125 centimeters. Charges are both 1 nanocoulomb. So the formula for E is kq over r squared. So we know this distance here is 5 centimeters. We know this distance here is the square root of 125 centimeters. We know both of the q values, and we know k. So we can find E1 and we can find E2. E1 and E2 using this formula. So plug in your 9 times 10 to the 9th, your 1 nanocoulomb, the nanocoulomb, and that's going to cancel. Let me do some quick math here. It's going to be 9 divided by 0.0. Oh, no. Divided by the square root of 125 squared, which is 125.0125. Whatever you get, 9 divided by 0.0125. And over here you're going to get 9 divided by 5 squared is 25, so 0.0025. I might be off by one digit here. Sorry. That's a bigger distance, so you're dividing by a bigger number. No, I think that seems about right. Hell, I don't know. I tell you what, this one is right because 5 squared is 25. 0.05. 0.05. That one's right. This one, yeah, I think that's right. So type these two numbers in, and you'll find these two forces. To find this angle here, you're going to have to use tangent inverse of 5 over 10. And once you get that amount, then you can find EX and EY using sine and cosine. And I'm going to stop right here again for time. This lecture is getting pretty robust, and we're not quite halfway yet. So if you want me to finish this problem, or you're looking in your notes and it doesn't make sense, or you want to get more review, this is something I'm happy to do in class. Just let me know. But once you get these two forces, vector sum, review, chapters 5 and 6. Okay, key concepts from this section. Number 1, the electric field caused by a point charge points radially outward or inward, depending if it's positive or negative. It points away from positives and towards negatives. We can add vectors at different angles. That's very important to break them into their x and y components first. Anything that's in neutral or in equilibrium should have a net force of 0. So a lot of times you'll have to balance, say, an electric force with a gravitational force, or pushes and pulls, things like that. A parallel plate capacitor is two parallel plates, one charged positive, one charged negative, and it creates inside of it a uniform electric field pointing from the positive towards the negative. This is very useful for doing experiments where you need a uniform field so you can test things out. Don't ever forget F net equals ma. It's been a little bit away from that in the past unit on optics, but now we're getting a lot back into forces, force diagrams, calculating the trajectory of particles, the position, the velocity, the acceleration, etc. And just keep practice working with variables instead of numbers, rearranging the equations using variables and plugging numbers at the end. Okay, so right now I want you to take a mandatory break. Mandatory. So go get some water, go, I don't know, do something. Alright, welcome back from your break. Hope you're refreshed and rejuvenated. So we talked a lot about forces and their relationship to the electric field. We're now going to transfer that information into energy and a new kind of concept called electric potential, which is typically called voltage. Also, there should be an E right here. I guess this is off the side of the screen, but you spell voltage with an E. I apologize for that. Okay, let's get going. So first, an analogy between gravitational potential energy and electric potential energy. So if you were to raise a brick higher and higher and higher and drop it, when you lower it, it loses potential energy. When you raise it, it gains potential energy. So there's some property of the brick, in this case the height, which is telling you how much potential energy it has. So electrical charges behave the same way, except instead of actual physical height or distance raised, it's this kind of abstract or conceptual height. When you bring it closer to a positive charge will have to gain energy because you had to push it in that direction, right? If you have a positive here and a positive here, if I want to lift this positive higher, I'm going to have to push it or do work on it to raise it, and then therefore it's going to gain energy because I did work on it. Likewise, if I had a negative up here, the positive charge, it would naturally go that way, and so instead of gaining energy, it's going to lose energy. So whether something gains or loses energy depends on whether it's naturally going that way, if that's the same direction the force is, or if it's opposite of the direction of the force and you had to push it or do work on it. Okay, so an easy way to remember this is, if the objects would naturally attract each other, then they're going to definitely lose potential energy when they come together. But if they would naturally repel, they're going to gain energy because you had to force them together by doing work on them. So, for example, if a brick falls to the surface, it's losing potential energy. When a positive gets pulled towards a negative, it's losing potential energy. Okay, so how much energy is actually stored by a configuration of 2 point charges? Well, mouse here. So we have to push this guy. So right now, the 2 charges are being repelled. So to get them to come together, we have to take this guy and we have to push him this way. Okay, so it takes work, force times distance. It's going to cost us some amount of energy to get them to come together. Okay, so it doesn't matter if we have absolute values for Q1 and Q2 because energy is just a number, not a vector. You're going to figure out whether it's positive or negative by using common sense about whether you had to push them together or where they naturally went together. But the effect is, once you push these 2 charges together, the amount of energy stored is proportional to the 2 charges. So if the charges are bigger, obviously you have more energy stored, but also it depends on the distance. So if they're closer together, the radius between them is smaller, you'll have more energy. So this formula is pretty similar to Coulomb's law, but instead of having r squared in the bottom, it only has r to the first power in the bottom. Again, it's kind of like force times distance. It's like you multiplied by d. So if you take k q1 q2 over r squared, that's your force, and you multiply by distance, so that you have work equals force times distance, right? And potential energy is what you get when you do work. So this is an analogy, this is not perfect math. The work causes potential energy to be increased. The force that you're overcoming is the Coulomb electric force, and the distance you traveled is distance. It's kind of like one of these r's canceled out with this d, right? That's what it looks like. So now you have r to the first power instead of r squared. Sorry, distracted by my dog. In reality, what you have to do is not just multiply these two, but you have to do an integral. And so it requires a bit of calculus, and it's a coincidence that it comes out to be exactly the same as if you just multiplied. So in this formula, Q1 and Q2 are the two charges, and R is the distance between them. So the closer they are, the more energy is being stored. Okay. So now let's define the potential at a point. So it's not energy, it's just the potential. Okay. So this we're going to call voltage. Some textbooks call it potential, some call it electric potential, some call it voltage. I'm going to choose voltage because that way there's no confusion between potential energy and voltage. So voltage is the equivalent or analogy to the height of a brick. For example, the higher the brick was, the more potential energy it had. For charged objects, the higher the voltage is, the more potential energy that they are storing. So the voltage of any charge is defined as the total amount of potential energy it has divided by its charge. Okay? So to derive this formula, it's very similar to how we derived the formula for the electric field was the force over the charge. So we're going to take the formula for force, which is Coulomb's law, and then we're going to divide off a Q to get the electric field. For voltage, we're going to take the formula for potential energy electric, which we just derived. We're going to divide off a Q, and we'll end up with voltage. So the derivation is here. If you are not interested in following along, you don't have to. I'm not going to talk about it right now. I'll talk about it in office hours if you want, but you can read through, pause and read through. So the net effect of all of that is that for point charges, really important to keep this in mind, for point charges, the voltage around a point charge is K times Q divided by R. That's only true around a point charge because the field decreases the electric field decreases radially as you get farther away. But in general, what's always true is that the potential energy is equal to the charge times the voltage. So if you know the voltage that a particular charge is at, whether it's because of a point charge or it's because of a battery or it's because of some other thing that it's plugged into, if you know the voltage, you know how much energy the charge has. So that's very convenient. And then likewise, if you rearrange and divide both sides by Q, you got the formula to find the voltage. So if you know the energy, you can find the voltage, and if you know the voltage, you can find the energy. So it's really important in your head that you get these things connected. Energy and voltage go together. Force and electric field go together. So the analogy between them is the same. Alright, problem solving tips. Interestingly, just like with height and potential energy, we had to define a reference point. So saying how much potential energy something has doesn't really give you any information, because the only way that anything actually really happens is by having a change in energy. So, I could say that right now I've got 5 billion joules of potential energy if I measure relative to the center of the Earth. But unless I can actually fall to the center of the Earth, I'll never be able to get that energy out. So the energy amount that I can get out from the potential energy depends on both the initial and the final positions. So with voltage, it's only the change in voltage that actually matters. It's not the actual value. So if something says danger, high voltage, and it says it's at 5 billion volts, well, that could be dangerous, but only if those charges have the potential to go from whatever they're at down to, say, 0. So a high number is only a high number if it has the potential to be compared to 0 or some relatively low number. So when we write the formula for potential energy, instead of just writing PE equals QV, we typically write a change in potential energy equals the charge times the change in voltage. So it's the amount the voltage changes by that matters. So if you went from 1,000,000 to 1,000,005, you're not actually gaining very much energy, whereas if you went from 0 to 100, you'd be gaining a lot more energy, and therefore you'd get shocked or whatever would happen, would be a significant difference. Sorry, you wouldn't get shocked. That's totally different. That was a not Freudian slip, whatever. Mental slip. You would not get shocked if you raised the voltage of a couple of charges. Alright, so the units for energy, it's kind of a different topic. Units for energy are joules because they're energy, but typically it's good to have this conversion factor between electron volts. So if you move a single electron through a potential difference or through a voltage change of exactly 1 volt, it will gain an amount of energy equal to 1 electron volt, which is kind of convenient. So if you put the charge in electrons and the voltage change in volts, then the units you get out would be electron volts. So this is very common because when you're shooting electrons, well, when you're doing experimental physics, you try to shoot a few electrons at a time, and typically you put them through a certain voltage to accelerate them, and so electron volts are a common unit. As much as I'll say about it right now. So you got to be able to convert between electron volts and joules. To do that, you have to convert between electrons and coulombs, which, lucky for you, you already know the conversion factor. So electrons to coulombs is the same as electron volts to joules. So 1.6 times 10 to the negative 19th is your conversion factor. Okay, sample problem converting units. How much energy does a proton gain when it is pushed through a potential difference of 50 volts? So say it starts at 0 volts and it ends up at 50 volts. Then the delta potential energy equals Q delta V, which, if it's a single proton, its charge is 1e and it's 50 volts. So you can see that the energy that it gains is 50 EVs, or electron volts. So that's why electron volts are such a convenient unit, and that's why people use them, is because it saves you from having to do calculations. If you want to then convert that, you have to multiply it by 1.6 times 10 to the negative 19th. Sorry. And then that will actually give you the amount of joules, which, whatever you type in your calculator, you get. Okay, sample problem 21.3. It takes 3 microjoules of work to move a 15 nanocoulomb charge from point A to B. It takes negative 5 microjoules of work to move the same charge from point C to B. What is the potential difference between, oh, this says C and B, but I think it should say A and C? Yeah. VC to VA. I apologize. Let's draw a little picture. So we got A, B, C. 3 joules of work, so 3 microjoules to move from A to B. So that means B is at a higher voltage than A. And it takes negative 5 microjoules of work to save the same charge from C to B. So going this way was negative 5, which means going this way would be positive 5, right? Does that make sense? So the net difference between here and here was 8 micro, well, that's supposed to be a J for joules. So delta potential energy total is positive 8 microjoules. Again, what they tell us is it's negative 5 to go from C to B. So from B to C, the other direction, opposite direction, changes the sign. It'll be plus 5 joules. So we got 8 joules, and that's got to equal Q delta V. So divide both sides by Q, divide both sides by Q, and we get the change in voltage from C to A is 8 microjoules divided by the charge, which is 15 nanocoulombs. Joules per coulomb is volts, so that's good. So 8 micro divided by 15 nano, that's around, I don't know, 500? Around a little over 5, so probably 550 volts. Cool. So it's just some practice using these formulas. One more sample problem, see what we have left. So one more sample problem, then we'll take another break. This is probably the biggest section, or the biggest chapter in all the rest of the year, but we'll take it in by section because there's a lot of different concepts that are being talked about. All right, an electron with initial speed 500,000 meters per second is brought to rest by an E field. the electron move into a higher or lower potential? Okay, so let's start with this guy. He's moving really fast, which means he has a lot of kinetic energy. Okay, it's an electron, so it's a negative charge. Okay, if it's going to be slowed down and brought to rest, that means that it has to be going, it has to be losing energy, which means the force on it is going to be this way, right? The force is going to be against it, slowing it down. But it's a negative charge, which means the E field has to be pointing that way. Because remember, the force on a negative electron is opposite the E field. So if the E field is on this side, the E field points from high voltage to low voltage, and therefore the electron is moving into a region of lower potential, aka voltage. So I changed most of the words potential to voltage, but might have slipped through one or two. So the electron must be moving to lower voltage. So naturally the electron would move to higher voltage, which means it would be speeding up, falling if you will. So here it's doing the opposite, so it must be going to lower voltage. What is the delta V that stopped the electron? Okay, so we know that the kinetic energy initial has to be converted to potential energy final. Kinetic energy it starts with is 1/2 mv squared. Potential energy it ends with is Q delta V. And we're solving for delta V, so we divide both sides by Q. Okay, so we get 1/2 the mass of an electron. I gave this last slide, but if you don't remember, 9.11 times 10 to the negative 31 kilograms. The velocity initial, 500,000 squared. And the charge on an electron is 1.6 times 10 to the negative 19th coulombs. Okay, so type all that into your calculator, and you will find out the delta V that stopped the electron. Okay, it says, what was the initial kinetic energy of the electron measured in EVs? So this is actually kind of cool. Because if it just said in joules, you'd have to do 1/2 mv squared, which you could do and get the answer. But because it says measured in EVs, you just found the voltage, whatever you got right here. So the energy in electron volts is just that number, EVs, because you take the voltage, which is that number, and you multiply by 1 electron. So the value, the numerical value stays the same. You just change it from volts to electron volts since you had 1 charge. So your final answer in electron volts would be that number. Kind of cool. Okay. All right, let's take another break. Sorry, I need to break myself. So I'm going to take a break. And when we come back, we will finish this thing off. We just got about 1/3 left to go. And then we'll be done with this beast of a chapter 21. Okay, let's see what we can do. Equipotential contours. So if any of you guys have ever done a lot of hiking, you might have seen what are they called? Equal altitude contours? Or just maybe a contour map. Let me show you the picture real quick. If you've seen a map like this, you know what I'm talking about. Let me go back. So an equipotential contour is basically a traced out shape or outline of places that all have the same voltage. So the key here is that every point along that line has the same voltage, so there'll be continuous closed circles that will close on themselves. And the reason that they're important is because you only have to do work on something if its energy is going to change. So its energy only changes if its voltage changes. So an equipotential contour is a line that you can essentially have a charge move across without actually costing any energy. Kind of like if you're hiking, you don't want to hike uphill or downhill. That will change your energy. But if you go at a constant height, you can do that without expending any energy. I mean, not really hiking. You still expend energy, but the idea is you're not gaining potential or losing potential energy. So it's kind of cool, equipotential contour. So it's like a contour map, but instead of having it represent altitude in meters or feet in terms of height, you're looking at the height in terms of voltage. So higher places have more voltage, which means they're located near positive charge. So positive charges are going to be at the peaks or the highest points, and negative charge would be at the valley or lowest points. So here's a picture of what a map might look like. So you might have like the top of hill here could be positive charges, and then down at the bottom could be negative. In fact, no negatives because it doesn't go below 0, but the cool thing about maps like this is the steepness of the hill is telling you the electric field. So this is going to have a strong electric field because you're going from 0 volts up to, say, 50 or 60 volts in a very short distance. And so you're getting a massive change in voltage, which is a change in energy, which requires a big force, which requires a big electric field. Over here, you have a very gradual change, so this is going to be a low electric field. So that's kind of cool. If there was a charge in here, it could get stuck in a stable equilibrium, oscillating between these 2 points, just like a ball with gravity. Charges with electric fields can get stuck in stable equilibrium positions. Let me zoom back a few slides to the beginning one of this second half of the lecture. I just want to remind you, this right here is actually an equipotential contour diagram. So if you have a positive charge up here and a negative charge down here, any positive charge is going to be pushed away from this guy, so it would be pushed downhill, like away. And any positive charge on this side here would fall, so to speak, fall down here because it's drawn towards the negative. And then these kind of brighter blue circles are the equipotential contours. So it's kind of neat. You can get very cool kind of three-dimensional shapes that show the way that charges will move. By making an analogy between that and gravity. So if you think of gravity as pulling things down, a charge will behave the same way on this equipotential contour. Okay, so sample problem, equipotential contours, lines of constant voltage. Find the potential contours around a point charge. So if we just had a positive charge here, okay, well, the formula KQ over R, in order to have the voltage be constant, K is constant and R is constant, so the only way to have the voltage be constant is to have R be constant. The formula, R equals constant, if you remember from math class, in polar coordinates, R equals constant is just a circle of a certain radius. So if the R is, say, 1, you get that. If R is 2, you get that. If R is 3, you might get that. So around a single point charge, positive or negative, your equipotential contours are going to be perfect circles going around. And in 3 dimensions, they'll actually be spherical, perfect spheres around it of constant voltage. And to find the numerical value, you'll just plug in K, Q, and R. So I'm not going to do that, but just concept in your head. Now, if you have 2 different charges, say 2 positive charges, I'll try to draw this one for you. It actually looks pretty cool. 2 positive charges. Your equipotential contour is going to look kind of like this, like a peanut shape, and then the next one will look like this. When you zoom out really, really far, so if you have positive here and positive here, if you zoom out really, really far, it looks kind of like just one bigger positive charge, so far, far away you just have perfect circles going around. But when you get in really close, that's when you kind of get this curvy shape. Does that make sense? So I hope it does. So this is the same as this, just and as you get farther away, the amount of that kind of bendy, curvy stuff, it gets less and less and less, and when you're really far away, it's almost just like a big circle on the outside. All right, now to the fun part, relating the voltage to the electric field. So these 2 concepts, they seem kind of maybe different. Voltage is related to energy, and electric field is related to force. But ultimately, you have to remember, everything we're learning in all of these chapters comes from the single fundamental principle that positive charges repel each other, and positive and negative charges attract, or opposites attract and like charges repel. Every single thing can be brought back to that basic principle. So these 2 things, electric field and voltage, are actually very closely related. So the E field and the equipotential contours are always perpendicular. This is the same reason as the E field was perpendicular to the surface of a conductor, because if it's not perpendicular, there's going to be a force side to side, and if there's a force side to side, the particle will move, and it will therefore gain or lose energy because there's a force over some distance. So equipotential contour is the same voltage everywhere, which means there's no force required to move around there because potential energy equals change in voltage, which is 0. So work equals delta PE or work can cause a change in potential energy, which would cause change in voltage. So equipotential contour, this is 0, this is 0, this is 0. If the work is 0, then the force must be perpendicular to it, because otherwise it would be doing, I guess we can do force times distance. If these two things are perpendicular, then they're not going to have any motion. Second thing, the E field points in the direction of decreasing voltage. We actually kind of already discovered that in the example problem we worked out a couple slides back. The E field points in decreasing voltage because it's pointing in the direction that positive charges would naturally want to go, the direction that they'll be forced, and positive charges will go towards lower voltage because they'll go towards lower energy, because that's the direction of the force, because opposites attract and like charges repel. Lastly, if you have a uniform electric field, then its strength is going to be proportional to the change in voltage divided by the distance. So if you have a big change in voltage in a very small distance, that's going to require a huge change in energy, which is going to require a huge force, which is going to require a huge electric field. So this third kind of result right here is because of this diagram here that I was talking about. If you have a big change from here all the way up to here in a relatively small distance, this slope is going to be steep. It's going to be a high electric field. Okay, so there's some proofs for those previous three equations. Again, I'm not going to go through these right now to save time, but you're welcome to pause and read them and then ask questions in class. So 3 proofs. Okay, so recap those 3 most important things. The electric field and the equipotential contours are always perpendicular to each other. Number 2, the electric field points downhill, which means towards lower voltage. And the electric field, for a uniform electric field, this is important, so add this to your formula here. For a uniform electric field, you've got delta V over D, which therefore, in a uniform field, the potential difference is the electric field times the distance. Cool. So some consequences that we've already talked about but are good to put into your memory bank. Positive charges go with the E field towards lower voltage, and negative charges always go opposite the E field, naturally will go opposite the E field towards higher voltage. So if you just drop a negative in the middle of a equipotential or into a voltage situation, it'll zoom towards the highest voltage. If you drop a positive charge, it'll zoom towards the lowest voltage. Just like if you drop a ball on a hill, a ball with positive mass will roll downhill towards the lowest height. And if you could kind of wrap your head around the idea of a ball with a negative mass, it would float upward to the highest point possible. Sample problem. You've got a negative 1000 volts coordinate system. At -1, you've got negative 1000 volts. That's negative 1 meters. Over here, you've got 1 meter and positive 1000 volts. Find the electric field, assuming that it's uniform. Okay. So positive towards negative, the electric field is going to point this way, because a positive charge would naturally move from a high voltage towards a low voltage. So you've got the strength of the electric field is delta V over D. Delta V from 1000 to negative 1000 is 2000 divided by, from 1 meter down to negative 1 meter is 2 meters. So you've got, that's volts. So you've got 1000 volts per meter as your E field strength. And now is a good time for me to point out something I should have pointed out earlier, which is there's 2 different units that you can use for electric field. One is newtons per coulomb. That's probably more common because that's what you get when you think about it in terms of forces. But the other thing you can use is volts per meter, which is what you get obviously here when you're looking at difference in voltage and charges moving through different voltages. So either one is acceptable and they're mathematically equivalent, which I encourage you to prove to yourself just using unit conversion factors. Okay, so massive recap of all of this stuff. And then like one new thing, I think, one slide of new things, and we're done. But this recap is something that you might want to come back to later on. So mark where it is or highlight this stuff in your notes. Make sure you have all of it condensed in one place. It is everything you need to know. Okay, forces on charges. We've got Coulomb's law, F equals K Q1 Q2 over R squared. Opposites attract and like charges repel. If you have more than one set of charges in your problem, you can find all the different forces and then add them up using vector components. Next, we talked about electric fields. So any charge, if you place it into an electric field, it'll feel a force, just like any massive object in gravitational fields will feel a gravitational force. The strength of the force that the charge will experience is equal to the charge itself times the strength of the electric field. Okay? The direction is the same as the E field on positive charges and opposite the E field on negative charges. Okay? The E field itself is not caused by that particular charge, it's caused by everything else around it. So the net cumulative effect of everything else around it is going to cause a particular E field, which will cause a particular force on any one given charge. And the E field of all those other charges, each individual one has its own E field, which is given by this formula here. The electric field for a point charge caused by a point charge is kq over r squared. So you'll have to find all these different ones and add up the vectors. So finding the electric field for a distribution with lots of charges in it is really, really hard, and typically you would use a computer for that. You'll be responsible for doing very simple ones like a single positive charge, a single negative charge, maybe a positive and a negative next to each other, or maybe two positives or two negatives. Anything more complex than that gets almost impossible to do by hand. Okay? Potential energy and voltage. So because positives will repel other positives and negatives will repel other negatives, if you put two positives or two negatives near each other, you had to do work pushing them together, and therefore they will store energy. So the amount of energy they store is given by this formula here, k q1 q2 over r. It's very similar to the force one, but it's r to the first power, not r squared. Okay. The voltage at any given point is proportional to the amount of energy it has, and so around a point charge, again, these are all for point charges, q1 and q2 point charges, voltage around a point charge, it's kq over r. And the amount of voltage at a given point is related to the amount of energy at that point. The energy equals the charge times the voltage. But since typically the total amount of energy doesn't matter, it's only the changes in energy that matter, more commonly we'll refer to this equation by delta PE equals Q delta V. Okay? So that's a recap of the most important things we've covered. Voltage and energy here, force and electric field here. So these four things are all related to each other. And on your formula sheet that I've given out at the beginning of class, there's a big grid with the four squares. One is force, electric field, energy, and voltage. So it's got the four formulas you need, plus all the ways to get from one formula to the next. So maybe you want to go from electric field to force. What formula connects those two? So four important formulas in the middle with connecting formulas around the outside. So that's a really, really good study tool for you to have on hand. Okay, almost done. Capacitance is a property of objects to store charge. So you might have heard of capacitors, or if you looked at circuits or things like that, you've seen capacitors. If you're in guitar building, you'll see there's a capacitor on there. And it tells you how much charge the object can store when it's plugged into a certain voltage. Okay, so you take the total amount of charge divided by the total voltage that it's plugged into, and that gives you the capacitance. So the higher capacitance, the more charge something can hold per volt, so to speak. And this is important because obviously if you raise the voltage, more charges, there's going to be a bigger electric field, and therefore more charges will move. But it's not, you typically don't want to have really high voltage scenarios, because if things go awry, it can fry stuff. So you want to be able to, if you want to store charge, you want to be able to store a lot of charge at a low voltage, so you want something with a high capacitance. We'll talk about how capacitors are made, but typically a very common one would be a parallel plate capacitor. So just two flat parallel plates, one positive, one negative. They'll form an electric field inside, and you can store that charge and then reuse it later on. So it's a way to store charge and then reuse it later on. That's what the purpose of a capacitor is for. Okay, sample problem I'm going to skip. Energy stored. So how much energy is actually stored, and can you get back from a capacitor? So to charge the capacitor up, we have to move the charge from one plate over to the other plate. So that requires applying a force to these charges to move them across. So the first charge you move over, it doesn't cost any energy because there was two neutral plates moving one charge. There's no electric field. But as soon as let me draw a little picture here. So the first little charge you move over here, say you move a positive here, and you leave behind his partner, the negative guy. Now there's an electric field pointing this way. So the next one that you move, it had to overcome this electric field, which means you had to do work to push it. And that creates an even stronger electric field. So the next one, the third one that you move, has to overcome an even stronger electric field. And every time you keep moving more and more charge across from one plate to the other one, excuse me, excuse me, as you keep moving more and more charges from one side over to the other side, you keep having to do more and more work because you're overcoming a bigger and bigger electric field. And so it's not going to be linear, it's going to be quadratic in terms of how much energy is stored. So the amount of energy stored depends on how much charge we move and the final voltage on the plates. So the voltage increases over time. There's a factor of a 1/2 here because if you graph it, it makes a triangle because the first one you move requires no energy. The next one requires more and more and more and more and more because as you move them, the force that you're overcoming is getting bigger and bigger and bigger. So this is going to be an increasing slope, and then the shape here is a triangle. That's a very ad hoc way to explain it, but just trust me, I guess. Ask in class if you want a better answer. Why there's a factor of a 1/2 in front. Okay, this is important because the potential energy for a single charge moving across a voltage is Q delta V. Okay, so be careful that you don't get these two formulas confused. These are not the same. They are not equal. For a capacitor, you're